Hey there, it's Modern Retro Tech, and today we are continuing with Advent of Code. We will be reviewing days 11, and we will be doing days 12 and 13 live. And we will also look at some Rust metaprogramming and our cool custom REPL interface that I was improving a bit during the weekend. So let me start with the REPL stuff because it's quite fascinating. It was my first time trying Rust metaprogramming, specifically macro rules stuff. As you may recall, I had this REPL definition where I needed to define each module for each day. So for example, that's the module for day 1. And here we have solve and solve2 functions. And then I had a list, essentially a static list with this signature commands where there were static strings and solvers, where solvers are just pointers to functions. So this type. And then I needed to specify a count of commands I define. That allowed me to then use cargo run to run my modules and get answers to Advent of Code puzzles. Now, one problem with that was first I needed to write those modules every time by hand, like doing all the boilerplate. And also every time I needed to add new entries in this list, recount stuff, etc., which is a bit annoying, of course, because that requires you just doing manual work. And if you forget something, it can be annoying to find the error. That was one thing. Another thing, I needed to write boilerplate every time by hand. So I needed to write those functions. I needed to define this tests module, etc. I decided to fix both of those. And one thing that I did, I defined this custom macro called commands. And here is how we use it. So here I still need to list modules, but then all the building of the list with like references to functions I need to call is done automatically. And I also copied somebody's cool macro called count that allows you to count a number of identifiers in this list. So in essence, all my magic is pretty simple. Count works recursively. So if you pass empty thing there, it just returns 0. Otherwise, it recursively calls itself with adding 1. And the list of commands is created by this commands macro. It takes any number of repetition of module identifiers. It counts them to specify a correct type for the array. And then it just stringifies the module name as the first element of a tuple. And then it creates a function that it will call when I call this module name. And it does the same for the day too. Now, another cool thing that I did before, my modules, they were all required to always return option of I64. I changed it to be option of box of any debuggable type. So in this case, it's I64. In this case, it's usize, etc. You can return strings, you can return whatever you can print to console, essentially. How do I put them in one list? That's another thing. Because here you can see that I just call my module and then I call the solve function, but those functions will have different types. Now, Rust is statically typed language, which means I cannot create a list of items of different types. But I can cast them to trait objects, which are box of dynamic trait object of debug trait. And then it will work. Now, one cool thing that's still in the day modules, I have concrete types. So in my tests, for example, I can do comparisons, I can do operations specific to this type. But in my REPL interface, the only thing I need to do is print them. And I can do that easily via doing this cast. And that essentially allows me to define both the list and the module definitions themselves that are required by Rust type system. Here, I'm doing that with this macro. That is one thing that I did. Another thing was to also allow listing of all the commands we defined. So I also have list command that just outputs all the commands that are currently available for like those days. I think it's quite self-explanatory how that works. we just go through the commands hash maps that we built from this commands list here. And here, by the way, we can also add custom commands, which is important for day 11 specifically. Yeah, so that was another feature that I added. And finally, I also added another thing, which is auto-generator of new modules. So as I said before, I needed to write this boilerplate where I defined stuff. Pretty much this is the template I'm using. So now I can just call next, and we will generate already day 12. And you can see that that command added the day 12 module here. So this is my boilerplate. It added an empty file for input for day 12. And it also added, it changed also the main function itself, adding here day 12. So essentially the whole thing is now automatic. I can close my REPL, I can run it again, it will recompile, it will show that those things are not yet used. But now when it finishes compiling, we can then call D12. It of course returns none yet because we didn't implement anything. And we can also run tests. So again, you can get those warnings because we didn't implement anything yet. But we can see that those tests are running. So that being said, let's do a quick review of day 11 and then start working on day 12 and day 13. So day 11, I will not go super deep into the task. I will just tell you that this task is essentially a game of life. So if you have not heard about game of life, just Google it. It's pretty well-known thing. It's very much this kind of puzzle. The only difference is that in this case, we have custom rules. So in the first part, the custom rule is that essentially if you have an empty cell, then it becomes occupied if there are no occupied cells around it. And if it is occupied and there are 4 or more seats adjacent to it that are also occupied, the seat becomes empty. We also have floors that never changes, which is also different from the game of life thing. In essence, you create a hash map with coordinates mapped to the state of the cell. And then on each iteration, you need to apply those rules to calculate a new hash map, and you proceed this way. In the end, you need to return how many seats end up occupied when the stuff stabilizes, and the new step returns the same thing as the previous step. I think it's easier to show how it actually looks. So if you go here, and we execute day 11. I also created this custom functions that also does debug for day 11. You can see that it uses the same visualization format. In this case, it's quite hard to read it. It even overwhelms my REPL, but essentially the limit of lines in my Visual Studio Code terminal. But you can see that it changes essentially with each iteration. We can also take sample input because then it's a bit smaller, and here you can see that it starts with everything empty and floor, then it changes everything to occupied, then parts of them change to be in empty and part of them change to be in floor, etc., until it stabilizes, and then we return the number of occupied seats. So that is part 1 of day 11. How is it implemented? Well, the top function here is a solve with debug, where we create layout. Layout is our custom type that has cells. So cells just map coordinates, which is row and column, to cell, and cell can be in one of 3 states. Since Rust has algebraic data types, it's very easy to define this kind of stuff. So we have floor, we have empty, we have occupied, and we have width and height of the whole layout that we have of the seats. Then we have a bunch of methods. We have parse method, parsing it from the input stream, which is pretty trivial. We have new methods that creates an empty layout with defined width and height. We have advanced method, and this is kind of the root of all the things that happens here. So that's the main part of the algorithm. This advancing accepts transition function, and this function takes a reference to a layout, coordinates for the cell we want to calculate transition for, reference to actual cell state, and it returns a new cell state based on that. So this is our transition function. Advance takes a reference to layout itself and its transition functions and returns a new layout. So new layout initially is initialized to be empty. Then we iterate through the cells, so through all rows and through all columns. And then we create coordinates for them and we get corresponding cell values. Then new cell is just calculated by applying transition function to the current layout, coordinates, and the cell states that we have. And then we just insert this new state in the new layout cells insert. For those who are joining now, we are solving Advent of Code. This is day 11 review. We will be solving days 12 and 13 live. Day 11 is pretty simple game of life, and I solved it, I think, on Friday. So just a quick review of that solution. So now, in part 1, this transition function is defined here. So this is our transition function. It has layout, it has coordinates, it has a cell, and we use a function called occupied neighbors that just calculates occupied neighbors. So like a number of neighbors that are occupied related to coordinates that we provide here for the current layout. We have a list of deltas, so those are like differences in coordinates in row and column for like all 8 neighbors that we have. So -1 is like top left neighbor, -1, 0 is like just left neighbor on the same row, etc. We go through those deltas, we create actual coordinates from them, and then we check that our coordinates are still within the layout, so they should be larger than 0, and we get corresponding cells and their state, and then we just filter the cells that are occupied, and then we count them. So pretty simple stuff here. Then we have this, we just match the cell states that we got. If it's floor, floor always stays floor. If it's empty and occupied neighbors equals to 0, we return occupied, new state, otherwise it's empty. If it's occupied and occupied neighbors is larger or equal to 4, then it becomes empty, otherwise it stays occupied. So pretty much what is described in our rules here, we can very directly encode in this transition function, which looks pretty cool, I think. Now, and then essentially what we do, we have previous layout, we execute a while loop, we check that either previous layout has not yet been initialized or it's not equal to the current layout. Then we take the current layout, put it in the previous layout, we create a new layout via layout advance and put it in the current layout, and if debug option is true, then we print it. So essentially, once we have previous layout and the current layout equal to each other, we can just count the occupied cells in the latest layout, and that's our answer for the first puzzle. So part 2 is about the same. The only difference is that instead of just occupied neighbors based on coordinates, we look for occupied neighbors based on visibility. So the moment you first find some empty or occupied seat, that's your neighbor, not like directly based on coordinates, but based on visibility. So if you have floor, you just need to skip it until you find some empty or occupied seat. And the rule changes a bit because for transition rule for occupied cells, it will be instead of larger or equal to 4, it will be larger or equal to 5. So here, transition function, the only difference is this, essentially, and this. We used visible occupied neighbors. And visible occupied neighbors use the same deltas as the normal neighbors, but we scale them. So we also have n. You can think about this delta thing as vector, and we just increase it by a certain factor, by multiplying it by this n, until we bump into occupied or empty seat. And then we break. And of course, if the seat is occupied, we add it to our count of occupied neighbors that are visible. And eventually, once we done with all the deltas, with all the possible directions in which you can look, we return the total count. And that pretty much solves the day. 11. So we can also take day 11 to debug, and you can see that it's slightly different, but overall quite similar. We got different number of occupied seats because of this visibility changes, but otherwise pretty normal game of life, I would say. So now we are done with reviewing stuff that we already did, and we can start looking at the stuff that we need to do today. I'm closing this stuff. We already have generated template for day 12. I haven't read the task yet, so I have no clue what's coming. I hope it will not be as complex as day 10. But yeah, so some reading of the task starts. Day 12, rain risk. Your ferry made decent progress towards the island, but the storm came in faster than anyone expected. The ferry needs to take evasive actions. Unfortunately, the ship's navigation computer seems to be malfunctioning. Rather than giving a road directly to safety, it produces extremely circuitous instructions. When the captain uses the PA system to ask if anyone can help, you quickly volunteer. The navigation instructions, your puzzle input, consists of a sequence of single-character actions paired with integer input values. After staring at them for a few minutes, you work out what they probably mean. Action N means to move north by the given value. Action S means to move south by the given value. E east, W west, Action L means to turn left the given number of degrees. Action R means to turn right the given number of degrees. Action F means to move forward by the given value in the direction the ship is currently facing. So we are going turtle graphics now, I guess. The ship starts by facing east. Only the L and R actions change the direction the ship is facing. That is, if the ship is facing east and the next instruction is N10, the ships would move north 10 units, but would still move east if the following action were F. For example, so forward 10, north 3, yeah. Forward 7, right 90, forward 11. This instruction will be handled as follows. F10 would move the ship 10 units east because the ship started by facing east to east 10, north 0. So our initial coordinates, I guess, east 0, north 0. And 3 would move the ship 3 units north to east 10, north 3. F7 would move the ship another 7 units east because the ship is still facing east to east 17, north 3. R90 would cause the ship to turn right by 90 degrees and face south. It remains at east 17, north 3. F11 would move the ship 11 units south to east 17, south 8. At the end of these instructions, the ship's Manhattan distance, sum of the absolute values of its east-west position and its north-south position from its starting position is 17 plus 8, 25. Figure out where the navigation instructions lead. What is the Manhattan distance between that location and the ship's starting position? Okay, so we need to move the ship according to the instructions and calculate Manhattan distance. Which is this? More formally, blah, 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 blah. Well, this shortest path. The green line has lengths and it's unique shortest path. Okay, sure. So we can, I guess, implement this quite easily. Let's copy our input. I can already see that I wonder if we got any like non-90 degree like if we get R and Ls that can be like not 90, 100 or 270 degrees. I would imagine not, because we are moving on the like this square thing. So that will simplify our stuff if this restriction really is correct. Let's, thankfully, we already used our REPL to create a new module. So we can start parsing stuff, right? How do we represent this data? As typical in Rust, we will first start with typing. So we will have command. Actually, we can just do enum, right? So, and each command will have like a different argument, right? So we'll have north, which will be, I guess those values, are they always positive? Seems so. Yep. So that will be then U32. That will probably be U32 too. U32. Then we will have south U32. Then we will have east U32. West U32. New joiners. This is Advent of Code day 12. We are solving part 1 now in Rust. Left is, for now we're just modeling the domain essentially. There'll be also U32 for simplicity. Right will be U32, and F will be forward, also U32. So actually I'm probably dumb. I should define a proper struct, right? I should say, let's call it instruction. Let's call this command, and this then command. I can just do it like that. So command and U32, because that I think will simplify our life a bit. Add cursors to line ends. Yup. So now we can derive a bunch of things here. I guess I will be super simple with that. I will make it a copy type, so I don't need to care about ownership much. And then I just need to define a parser as usual. So parse will take input, which is a string reference, and it will return a vector of instruction. Now input we trim, and as typical we split by new lines, and then we map each of those. So each of the lines becomes an instruction. I wonder if I can use trim for this. Actually, first character is always the instruction, right? So let command char is line. I wonder if this will work. Let's say none. For simplicity, adding this. No, it doesn't like it. So chars, char indices. Is there something like add or as bytes? Well, that will return. Well, I will just do chars, and I will collect it to also a vector. Those will be vector of char, yes, and then I can say actually thinking that we probably can do something with slices. Let me check it. So that's like iter blah blah blah. I want to just use indexes. Ah, there. Okay, that should work actually. Why didn't it? Maybe. Yeah, I can probably go here. Oh, yeah. So I'm just thinking that line slice 0 should be what I'm looking for, right? test command. Okay, this is so weird. I guess you really need to have a string thingy, because otherwise it doesn't like it, because it is unsized. So I guess, can I do this? Yes, thankfully. Okay, now so command then will be f will be forward. Yeah, we will need to use this stuff. Then what else do we have? Oops. North, south, east, west, left, right, and forward. Okay, yeah. So that's the command thingy, and what we need still is the number, right? So let how do they call it? Value, actions and value. Oh well, this is actions. I call it action. Let's call it action. Let's be consistent. So action char, unrecognized action, action, and then we have value, right? So value then is action let's just call it line for simplicity. So line, everything after first char. So and then we need to parse it as u32, and then we just unwrap it, right? And what we return then is instructions. Yeah, instruction where we have action and value. So that's our parser. What don't you like? In the current scope, can it do it like that? No, it doesn't. Oh, okay, sure. I guess. Why? I really wonder. Gosh. Join. This is kind of stuff that is always super annoying because what does it want from me? Okay. Take line, we take this stuff, and then what can you do? Okay, we need to Google this. Vector of chars to string Rust. Yes, thankfully. Into iter collect. Oh, okay. So we can do collect string, I guess. And then we can do into iter. And then we can do the whole parse stuff, I guess. Whoops. Yay. Finally. So, and then we can undo this. And now we can say instructions, it's parse of input. And now we can see if that worked already. So we can call our auto-generate test. Oh, yeah, of course, I didn't print anything yet. So let's add debug instructions here. so that we actually see what we are doing. And then we can call this stuff. So looks correct. Let's see. So we start forward 41, north 2, left 270, south 3, and we end up with forward 95. Okay, so parser is correct. I won't write test for that. I think it's quite simple. We don't need to care about it that much. So now is the main thing. We actually need to start moving stuff, right? So how do we move stuff? We parse this, we have instructions, and then we just can define a function, I think. Yeah, let's move this stuff. Oh no, actually, let's keep it here. Let's just continue writing it there. So now move, because, perform. So yeah, execute. So we take, we also will need to have a type for position, right? So type position is, in this case, we can end up with negative values, I think. Let's define a simple struct. So position, which will be I32, I32. I will even say this is like east and this is like north, otherwise you will get confused. So and this stuff then, what does it take? It take a reference to the current position. Let's go to pause for simplicity, and reference to position, and it take an instruction inst, and it returns a new position. And then, yep. So position stuff, let also make it this, because it's just two numbers, so we don't need to overcomplicate that. We have debug, clone, and copy on that. And then we need to execute. So one thing that we also miss in position is, by the way, the facing direction, which will be, for the sake of simplicity, should I actually use north, south, east, and west from action? That is not like very clean, but it's very simple. Let's do action, actually. Okay, it looks, it's a bit of a but since we don't have simpler ways of achieving that, and I don't want to spend too much code writing this stuff again, I will just say that only north, south, east, or west are allowed. What does this do? So, and of course we can create a new one. So position, new, returns position, and it will be position, direction. It starts with east, I believe. Yes, so east. And then it has east 0 and north 0, right? So then, depending on instruction, let's just match it. So match instruction. Let's deconstruct it. So this will be action value, right? And then match action. Oops, inst, of course. So with our action, what kind of stuff we can have? We have any of those, right? So you can just copy that stuff and put it here, and then, right? So our new position in case of moving north will be I think that's the copy syntax for structs as far as I recall. So I actually will just do pause here everywhere just for simplicity to make sure that it doesn't fail immediately. So we have this pause, and then what happens when we move north? We just change our north scene, right? So north becomes position north plus unit north 3. So it becomes north plus value. Is it correct? Something is broken. Where did I put U32? Of course, let's make it also for simplicity I32, though I know that it's not what we get there. Found position. Actually, we can just use this because we can always clone this stuff automatically, so it doesn't matter. Don't need to care about references here. Then for south, it's about the same. It's just position north minus value, I guess. Then for east, it's east plus value. And for west, it's minus value. And then for left, we only change direction. We don't change direction. Will be... Oh, so here it depends on value, right? So, gosh. Turn left. Value I32. Direction is action. No, it looks not very beautiful, but what can you do? Though actually, why I'm saying that it doesn't look very beautiful, because forward then will be super simple, right? We can just use the actions that we have in our direction. So if you have this, stop. So then value, we can just match it, right? So if it is 0, then we return direction. If it's 90, so we turn 90 left, which means left. Oh God. I'm so bad at this kind of stuff. So do you east and face south? It's east south. Okay. And in this case, if our direction is north, if we are facing north, we turn left by 90 degrees. It means we are now facing west. If we have south and we turn left 90 degrees, it means we are facing south. We are turning left. It will be to east, I believe. If it is west, actually that's probably better. So west will move to south, south to east, and east to north. Yeah, okay, so it's actually a loop, right? I probably can write it a bit simpler with like having a enumerator, iterator that has this values in this direction, but doesn't matter. Just say to do. Is it correct? Doesn't like it. Missing my charm. Valid direction. Yeah, it's debug, not display. And then I will just copy this stuff really. So 180, it means north becomes south, west becomes east, south becomes north, and east becomes west, right? And 270, do we even have 360? No, we don't. So we don't need to actually care. Do we have like left 0, right 0? No, so we actually don't even need this. And for this, we need to take this, and then it will be, so 270 will be like suck, suck, suck. So it will be one right? It will be then north will become east, west will become south, south will become east. No, south will become west, and east will become one right, north. Yeah, okay, looks correct, but this is of course, oh god, that will be crazy to QA. And then we also write really ugly function for turn right now. So turn right, 90 degrees, turning right. Right is here. So north becomes east, west becomes turning right north, south becomes turning right east, west actually, and east becomes south. Yeah, and 180. Well, it doesn't really matter, right, in which direction we turn, so same thing. For 180, it's just like opposite. 270, it's one left. So this will be then, or actually I can just copy it. So actually I can express it, right? I can just say turn left, where direction will be same and value just will be 90. So that will be simpler. And this then can also be turn left, direction 180. Like, does it matter? Right, left? No, it doesn't matter. Okay. So we can do turns. So here then left, we can do direction, which will be then turn left. We take our current direction and we take our value. Nothing fancy here. And for right, it will be exactly the same, only we will use turn right. And for forward, we can just call ourselves recursively, I believe. So we can take execute current position, and for instruction, we can take position direction. So that's where it pays off to have direction as action, right? Because then we can immediately just call ourselves recursively. Here, yeah, okay. So that allows us to move somewhere. We can now try to run it on our, let's do this. Let's say let input equals this stuff. And then we can say solve input. answer should be 25, right? Yes. But for now, we first need to do this moving thing. So what do? We take our instructions, and then for each of those instructions, we just move. So instructions into iter fold. We start with our position new. And then for each of those, I always forget the ordering of elements and arguments involved. First accumulator. So we take our position and we take our instruction. And then what we need to execute, we just call execute position instruction. So this is our final position. And now we can, I will just for now print it before I start calculating Manhattan distance for that. But I think it should be just the sum of those two, right? Yeah. Actually, I can already do sum final position ist plus final position. Yeah, we may be screwed by like negative numbers here, but let's see if we will be screwed by negative numbers here. And yeah, and this is then, of course, should we do absolute? I think, yeah, let's do absolute. And here we can do absolute. Doesn't matter which direction. What doesn't it like? It still doesn't like that it's SU32. Okay. Why? Oh yeah, we also need to do boxing now because of changes to the REPL that allow us to return different kinds of values from those functions. But that, oh yeah, and here of course it then will be box new as well. Here it doesn't like value. Found U32. Yeah, I32. Okay, I think here's another position direction. Instruction. Oh, yeah, we need to create instruction where we take position direction and the current value. So, same stuff. Okay, no more errors. I think we can call our test and see what it outputs. So, we got 17 and south 8. Yep, that is correct. And for the, here we got minus, so west 328 and south 238. But then our first test succeeded, right? So test, oh god, I always so confused about the notation here because it mixes up stack traces with all the other stuff. Do we actually have a third here? Let's check. That's easier to read, honestly. E. Okay, we can do this. Let's run it and see. Yeah, so that works. So the output we get here should be correct. Stop this one. So our answer should be 566. Let's see if that is correct. This is not the right answer. It's too high. If you're stuck, make sure there are also some general tips, or you can ask for hints on the subreddit. Okay, 566 is not correct. I wonder if we can check if our result here is correct. So it's not 566. So I guess that is excluded. And then we say I'm just adding this test so we don't accidentally submit the same wrong answer. So here we should get like the actual answer. Let's quickly test it also with our REPL to see that it works, because I'm wondering now. Second. So this is day 12. We got south. By the way, did we correctly calculate some of the absolute values of east-west position in its north-south position? Yeah. East-south. This location and this ship starting position. East, because the ship started facing east. Turn right and face south. Okay, so our stuff is correct here. Our final position in the at least test input was correct because it was facing south, and it was facing south, and it had correct coordinates as well, right? So when I execute this, we can see that we are facing south, east 17, south 8. Then our Manhattan distance is 25. Why, I wonder then? I feel that we probably screwed up in one of our turns, right? That's most likely things that didn't work out well. Sadly, there is only one test input. So let's see also on what we have here. So we have 90 forwards and stuff like that. We should probably add a couple of tests for turn right and turn left, right? Turn left 90, 90. So turning right, let's just try to read it. So turning right from north is east. Turning right from east, let's always put them in this order so we see that it makes sense. East is south, from south is west, from west is north. Yes? Yes. Turning left from north, we turn to west. Where, what do they have? They have right here with right and face it, ship turn and face south. So from east to south. Yes, okay. In case of left, from north we go to west, from west we go to south, from south we go to east, from east we go to north. North, south, west, east, south, north. Yeah, I'm just also trying to cluster them a bit. And east, west, makes sense. And here it's north, east, west, east, north. Oh, I think I found error. So north, if we turn left, north, east makes sense, right? 270 degrees. It's like 90, right? From east, we need to go to south. So, and by the way, this error is very easily corrected because we can also use turn right here. We can say those are mutual recursive function, but it's not as bad here because there's only one step of recursion, right? So now we can try to run the test again, and hopefully we will get correct answer now. Yeah, 508. So let's see. Yeah, we solved it. Okay. So let's make it now a proper test, saying that this should be equal to 508. And we can continue to part 2. Yeah, and I will also quickly remove this debug instruction because we don't need it. And I can also collapse those functions for now. So, part 2, day 12, advent of code, continue with our Rust stuff. Oh wow, it's even larger than usual now. So, before you can give the destination to the captain, you realize that the actual action meanings were printed on the back of the instructions the whole time. Almost all of the actions indicate how to move a waypoint, which is relative to the ship's position. Ooh. Action N means to move the waypoint north by the given value. Action S means to move the waypoint south by the given value. Action E means to move the waypoint east by the given value. Action W means to move the waypoint west. Action L means to rotate the waypoint around the ship left counterclockwise, a given number of degrees. Action R means to rotate the waypoint around the ship right clockwise, the given number of degrees. So right clockwise. Yeah. Action F means to move forward to the waypoint a number of times equal for the given value. I wonder why they write clockwise and counterclockwise here. Did they write it the last time? No. Okay, interesting. I guess because this will be confusing and source of bugs. To the waypoint a number of times equal to the given value. The waypoint starts 10 units east and 1 unit north relative to the ship. Waypoint around the ship left, around the ship. That is, the ship moves, the waypoint moves with it. For example, use the same instructions as above. F10 moves the ships to the waypoint 10 times. A total of 100 units east and 10 units north. Okay, so we again get like this vector multiplication stuff. I really probably should have a generic vector type already, because that will simplify this kind of stuff. Leaving the ship at east 100, north 10, okay? The waypoint stays 10 units east and 1 unit north of the ship. And 3 moves the waypoint 3 units north to 10 units east and 4 units north of the ship. The ship remains at east 100, north 10. So that moves 10 north of the ship, 3 units north. So it becomes 4 units north. Okay. And the ship remains in the same position. F7 moves the ship to the waypoint 7 times. So that then will be east 170, north 7 multiplied by 4, 200, north 38. Okay. Leaving the ship. The waypoint stays 10 units east and 4 units. R90 rotates the waypoint around the ship clockwise 90 degrees. So here we are. So it's like 2 points now, right? We have ship and we have waypoint is 10 units east and 4 units north. And then when we rotate clockwise 90 degrees, moving it to 4 units east and 10 units south. Oh. Okay. Well, it switches the directions again. The ship remains at east 170, north 38. F11 moves the ships to the waypoint, blah, blah, blah. After this operation, the ships may have the distance from its starting position. Figure out where the navigation instruction actually lead. What is the Manhattan distance between that location and the ship's starting position? Okay, cool. So we will need to check 2 points now instead of 1. I don't think it will be such a big deal for us, but let's try. I think there it's also important that we modeled our stuff already quite precisely, so I think it will be okay-ish to execute that. So now we have waypoint doesn't have direction, right? Point around. So we will have struct waypoint position. Actually, do we know anything about position? No, we don't. We work on actions here, which is really good. So waypoint position will be a new struct that we define here. That will have also we will define ship and waypoint, where we will have ship, it will be a position, and waypoint will be a position. We won't be actually using direction of the ship anymore, as far as I understand it. Actually, direction doesn't matter, but well, we will have another execute anyways. So we will have execute with waypoint, right? Which will take, I will collapse it a bit. Which will take this instead of normal position. And will take instruction. And will return this stuff. And for that, I will also implement a new method, which will be ist. So ship will start at the same thing, right? Total, yeah. So ship starts at 0, 0, I guess, and yes. Position new. And waypoint will be that will be position with east 10, north 1, direction, I guess also I will say east, but direction doesn't really matter anymore. And here we need to refactor stuff. So for now, let's yes. Position, yeah, it becomes ship waypoint. Yeah, we'll just do here to avoid this stuff. Ship and waypoint. So what happens when we have north? Action to move waypoint north by the given value. So we take ship and waypoint. Yeah, we don't need this. We take we take waypoint, and waypoint will be waypoint, but it will have north, yes, being waypoint north plus value, right? Yeah. So let's, oh, it doesn't like it. Why? Expected expression. Well, it is an expression. Why would you expect semicolon here? Oh, I guess this stuff doesn't work inside it, right? So you'll need to do this. Oh, okay. At least that's what I guess it doesn't like. No. Waypoint, north, plus value, and semicolon, yes. And here, well, by field access, well, it's not a cast. Oh, of course, I forgot to say that this is position, right? Yeah, okay. Actually, will it be more understandable if I write it like that? Let's see. Okay, that's okay. So that becomes more and more JavaScripty right now. Then for south, comment. It seems that my macro magic broke a bit this Rust analyzer, which is weird, but okay. So we can do ship and I guess that will be easy, right? We can do this. So waypoint becomes this, and otherwise it's so. And this is so waypoint. Yeah. And same with east and west. So So, and here we need to say waypoint, and here we need to replace it. Okay, and now we have, oh, of course, that we didn't want to do. And now we have left, right, and forward. Let's first do forward because I think it's the easy one, which will then be, so how does it work? Waypoint a number of times. So in essence, can we do execute? No, we need actually to use execute with ship, but using, can we use waypoint as instruction? 10 units, nah. We need to do some calculation here. So actually, let's do this. To prevent Rust Analyzer to collapse in my parentheses. Let's first do left and right because I think then I will grok it a bit better how we're actually doing this. So yeah. So with left and right, we also change waypoint, right? Yeah, we change waypoint. So and here, of course, I wonder if it will, well, it will not work, right? So like I can put it here to make it syntactically correct in the meantime, but this doesn't make much sense now because when we rotate, we need to rotate it around each other instead of just changing direction. So direction doesn't matter anymore. But turn left returns action, and I wonder, so they have an example here. So rotate 90 rotates the waypoint around the ship clockwise 90 degrees, moving it to 4 units east and 10 units south. Before that, the waypoint was 10 units east and 4 units north. So from north, our 90 should move it to south. If you look at north, south, clockwise 90 degrees. Okay, moving it to 4 units east and 10 units south. So you kind of switch this stuff. Oh, okay, that will be, I think it will be completely different function then, right? Yikes. I think we even need to do a different thing here, right? So we will just do waypoint in this, and here we will do then like to let waypoint equals to turn waypoint left. Like ship position doesn't matter. We just switch coordinates, I think. So we say, so waypoint, and we take a value, and that is it. And here then it will be another function that just does the same but right. And for now I just will do this. So it takes waypoint, which is position, and value, which is I32, and it returns new position, right? For now, just to do, and same with this thing. So for now, we're just making it compile as well. And Then with forward, what do we do that? So imagine that we implemented turn waypoint left and right for the moment. What do we do with forward? With forward, we need to take those coordinates and multiply them by the number in them. Okay, I see. So we just take let ship, which will be, right? So ship. And here then it will have east, and it will have north, and east will be so ship east plus so east multiplied by value, and north will be, I guess, same thing almost, but instead it will be north. Yeah. And then, so we got position here. And here we define ship and waypoint. We say ship, and waypoint stays the same, or yeah, waypoint stays the same. Actually, do this. Oh yeah, and of course position. So forward we implemented, but now we need to implement the most hellish one, waypoint left and waypoint right. So I will collapse this stuff for now. So we need to move stuff clockwise. What does it mean? Do we just move coordinates between them? So we have east and south. It means like we have point, we have ship here, we have this thing here, or north it was, right? Moving it to, it was 10 units north, 10 units east, and 4 units north. And then we rotate it 90 degrees and it moves here, becoming, instead of east coordinate becomes then south, yes, 10 units south, and north coordinate becomes east. Yeah, okay. So we just switch coordinates essentially, as far as I understand it. So we say value. Thankfully, we have this left and right thing that which should be right. So if it's 90 degrees, we match direction again. We match. No, we don't match in direction, right? We just say position where we have waypoint, and we say now east. So we have east becoming south, and so north is minus east, and east is 10 units south, 4 units east. And this is just north is just east now. So north minus waypoint east, waypoint north. And it's better to switch them, I guess. Right? Yeah. Then if you have 180, gosh, we need to think about it. So if you got east and north coordinates and we switch it clockwise once, clockwise twice, it becomes east became first south, then it becomes west. So I guess it's just minus, right? Waypoint north. Yeah, it's just like switching them, really, I think. Then we have 2080, or 270, sorry, which will be, by the way, I think it's still, we can use our nice symmetry here, saying that this will be waypoint, and value will be 90. And otherwise, we will just panic, saying this. Invalid value. Right? And here, we can define stuff. How did we do it? In turn right, I think we only needed to define, 180. Will it be still the same, clockwise and counterclockwise? Yeah, I think same. Yeah. So this will be kind of the thing then. Well, okay, I won't copy it directly. So this then will be turn waypoint left. Turn waypoint left 90. And we only need to figure out right for 90 now, right? So if we turn in stuff right, it means counterclockwise, which means if we have east and north, we will have east coordinate becoming our north coordinate, and north coordinate becoming our west coordinate. Yes, so minus. Okay. Oh god. This is like a thin transforms. It would have been easier if we had matrices and vectors, of course. But right now I'm just going like really manually with that stuff. So we did this, and now we just need to call this function. So we have waypoint now. So here, let's say final position is then instructions into iter, sure. And then we have different thing here, right? We have waypoint and we have our ship, but that we can create here. So say ship and waypoint, new. And here we have ship and waypoint, and we have instruction. And then we just call execute with waypoint, ship and waypoint instruction. Well, take two distinct, but it takes a single two tuple argument. Oh, sure. Sorry. Two distinct arguments. Can I actually just pass this stuff here? Can I do this? Yeah, I can. So actually that works. I can even do it like that here. That's pretty cool. So now, of course, we need to again check that our final position here makes sense. So let's do this and see. So that's our input. Let's make it a constant. Sample input will be a static string. In this case. So that should still work. I broke something. Doesn't implement. Oh yeah, sure. But by the way, I here. So struct. Yeah, do the same stuff here. So it will be debug, clone, and copy. So now hopefully part one will run. And here I just want to implement, execute it, gosh, on my sample for now to see if we get anything that makes any sense. So we got something. Stop. Oh, yeah, it's solve 2 we need. And our answer should be this, actually. So, yeah, by the way, I can just put this calculation here again to check both things already. Oh, what do we do? Oh, yeah, we need to calculate a different thing. The ship's from its starting position. So this will be so. Yeah, let's do so, and then we do so ship, so ship. Yes. Okay. Let's try again. So ship is east 126 and north 148. I don't believe it's correct. I think we screwed up somewhere. But waypoint east, well, direction we can east -4. Is it correct? 4 units east and 10 units south. It looks like we mixed it up here. We only have right 90. Okay, let's check our turn. Turn waypoint right. So right 90 should be east becomes 4 units east. East becomes gosh, it's so confusing. 10 units of the ship. So this become minus. Okay, that's the minus and that's the minus, and we mixed it up. So here, that's how it should be, I think. And now we should be correct, hopefully. So we got 214 and 72 south. Yes. And Manhattan distance is 286. Correct. Okay, so now we can execute it on our actual input and see what we get. So that's, let's see if that is correct answer. Yeah, we solved day 12, and now we will move to day 13. Yeah, we also need to add box here, so we have the test. I will quickly commit this stuff. And by the way, this is live, so if you have any questions about Rust, Advent of Code algorithms, feel free to ask. I will be glad to answer. So far, yeah, and also let's check that our tests run. Seems still everything is running, I think. Yep, it does. So yeah. So now let's see day 13. And by the way, even before we look at that, we can recreate our REPL and generate the boilerplate for it already. So that we won't need. You can say next, and you can see that we got the certain stuff already here. Okay, beautiful. Oops, day certain, of course, I want. Yep. So, day 13 shuttle search. Your ferry can make it safely to a nearby port, but it won't get much farther. When you call to book another ship, you discover that no ship embarked from that port to your vacation island. You'll need to get from the port to the nearest airport. Fortunately, a shuttle bus service is available to bring you from the seaport to the airport. Each bus has an ID number that also indicates how often the bus leaves for the airport. Bus schedules are defined based on a timestamp that measures the number of minutes since some fixed reference point in the past. At timestamp 0, every bus simultaneously departs from the seaport. After that, each bus travels to the airport, then various other locations, and finally returns to the seaport to repeat its journey forever. Ooh, not a nice working conditions for the drivers, I guess. The time this loop takes a particular bus is also its ID number. The bus with ID 5 departs from the seaport at timestamp 0, 5, 10, and 15, and so on. The bus with ID 11 departs at 0, 11, 22, blah, blah, blah. If you are there when the bus departs, you can ride that bus to the airport. Your nodes, your puzzle input, consist of two lines. The first line is your estimate of the earliest timestamp you could depart on a bus. The second line lists the bus IDs that are in the service according to the shuttle company. Entries that show X must be out of service, so you decide to ignore them. To save time, once you arrive, your goal is to figure out the earliest bus you can take to the airport. There will be exactly one such bus. For example, suppose you have the following notes. 9:39 is the time. 7 blah 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 buses. Here the earliest timestamps you could depart is 9:39, and the bus IDs is services are 7, 13, 59 blah. Your timestamp those bus IDs depart and the times marked D. So I guess 944 divided by 59 will be 16. Yeah, so those are, by the way, if we divide this by 59, we will get 14 or something like that. Okay, let's just do... This is the job for actual interpreted language, so 59. 16, yes, gosh. And of course, 936 is 13. So this is like based just on division, right? 72. Okay, the earliest bus you could take is bus blah blah blah. It doesn't depart until timestamp 9:44, so you would need to wait 9:44, 9:39, 5 minutes before it departs. Multiplying the bus ID by the number of minutes you need to wait gives 295. What is the ID of the earliest bus you can take to the airport multiplied by the number of minutes you'll need to wait for that bus? Okay, and yeah, 59 multiplied by 5. 295. Okay, splendid. Okay, seems like a comparatively easy task. We can just do divisions, right? We can take the starting position and then we can divide it by the bus IDs. Will it make sense? Or we can just like count from it up until we reach something. I think like doing loop, it will be a bit easier, but yeah, let's just do that. We need to copy our input in already pre-created file. So, and by the way, this is like, it's like 1,000,001. Okay. So in this case, our parser will be super simple as usual, but by the way, I probably need to add parse also to my template. Input string, and it will return. What will it return? It will return timestamp. Do we do struct? Yeah, let's do struct. I like structs. So task will be timestamp, which will be u32. And by the way, this stuff then will be u32, u32. And here we will have buses. Bus IDs actually, which will be a vector of u32s. Splendid. And parse just returns task. Actually, then this can as well be its method. Yeah, since I'm writing advent of code also to learn a bit of Rust, that's why I'm doing everything like a bit more with ceremony, with structs and stuff. I know that you don't need to do it, and most people don't do it for advent of code because especially if they try to compete in leaderboard. But in this case, I want to actually see how I can still write stuff comparatively quickly, but also maintainable to an extent. So that's kind of the approach I'm taking, and that's why I have so much structs and like all those modules and functions and tests, because I want it to be a bit more close to real world programming in this sense. So what do we do? Well, treatment, split by n. So we should get, as you know, I love this syntax a lot because it's very expressive. So here I can say timestamp bus IDs, and otherwise I can just panic unexpected input split. I want to debug to see what actually happens there. And then for timestamp, I just say timestamp what is type of this thing. I would imagine that parse will work on it. Just for simplicity, let's do this. So it doesn't like it. Cannot index into a value. Really? Or maybe, oh, I guess I will need to collect it, right? I need to collect it into a vector, and then I can index into it. So, yeah. And here, of course, it's a macro. So timestamp we parsed, and bus IDs will be bus IDs. We split that by how are they separated by commas. And in the end, it's just new line. Sure. We filter, saying that this is ID. ID should not be equal to X. And then we map. So each ID we map to parse. We say U32. We unwrap, and we then collect. And here I can even just skip that, because here I will write task timestamp bus IDs. It will know the type already. So what don't you like? I guess can compare blah 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 with blah blah blah. Sure. Now it's happy. Okay. I guess we parsed our task. We can do task parse input. And we can just verify that we parsed it correctly by adding debug here. And of course, we need to make it as usual. I'm just making a debug, clone, and copy for simplicity. It's just... Oh, copy I cannot make it because it has vector, sure. But debug and clone I can. So we can then run it and see that we parsed everything correctly. We can start also thinking about, so we got, yes, that's correct. And those 37, 29, 29, 37, 601. Yes, okay, so we parsed everything correctly. Now, part one, what we do, we just go from our timestamp and check if we have any bus that has 0 when we divide the time by it, right? So I will just even loop. I will just loop here. So we will break out of the circle with return, I think, where I will say, so task timestamp, be task timestamp. And then timestamp for bus ID in task bus IDs. iter. So this we just then do timestamp if timestamp divided by. I absolutely don't remember how to do module of division Rust. Modulus reminder. Okay, so I should it should be this operator. Opsram. Yeah, okay. Reminder is okayish for my purposes. So if timestamp reminder by bus ID is equal to 0, we know that minutes. This will be the earliest because that's the first one we visit, right? We then take timestamp minus task timestamp that is always lower multiplied by bus ID, that answer, right? And then we just do sum box new answer and we return the stuff. So that's the thing. And if not, what happens? We just say timestamp goes 1 second further, and that we don't need. And our answer for part 1 should be sum box new, and that should be 295. $174. That's not what I wanted to test, of course. That's my sample input. This is probably my solution. Let's just copy it here because we can check it later. For now, let's see, I put it here, I guess. Here, though, and I will just comment it out. 9. Toggle add line comments, yes. Here then, instead of this, we will make row literal as usual, but we will put this. So 10. Actually, so let's see, it should work. Yeah, it does. So I guess 174 should be correct answer, is it? Yeah, we solved it. Okay, that was fast. We can uncomment this stuff and then we can do part 2. Remove line comments. Yes. So, part 2. The shuttle company is running a contest. 1 gold coin for anyone that can find the earliest timestamp such that the first bus ID departs at that time and each subsequent listed bus ID departs at that subsequent minute. The first line in your input is no longer relevant. Okay, for example, suppose you have the same list of bus IDs as above. An X in the schedule means that there are no constraints on what bus IDs must depart at that time. Also, that's like different interpretation now, right? This means you are looking for the earliest timestamp called T such that bus ID 7 departs at timestamp T, bus ID 13 departs 1 minute after timestamp T. Oh god, I think I know what it is. It sounds like this integer division problems that are used in ciphers, right? Hey, bus ID 13 departs 1 minute after timestamp T. There are no requirement for restrictions on departure at 2 or 3 minutes after timestamp T, bus ID 59 departs 4 minutes after timestamp T. 0, 1, 2, 3, 4. There are no requirements in section departure of 5 minutes. Bus ID 31 departs 6 minutes after timestamp T. Bus ID 19 departs 7 minutes after timestamp T. The only bus departures that matter are listed bus IDs at their specific offsets from T. Those bus IDs can depart at other times, and other bus IDs can depart at those times. Can depart at other times, and other bus IDs can depart at those times. For example, in the list above, because bus ID 19 must depart 7 minutes after the timestamp at which bus ID 7 departs, bus ID 7 will always also be departing with bus ID 19 at 7 minutes after timestamp T. Will always also be departing with bus ID at 7 minutes after. Okay. For example, the earliest timestamp at which this occurs is blah blah blah, very big number, I guess. Well, not super big, just million, but still. We have way more numbers. So this number should be divisible by all things that we have here, right? So if we divide it by, if we divide it by 7, if we divide that by 13, actually I can just do it. Oh no. Yeah, because there are also shifts. It's even different. It's like we are not only need to calculate that, we're like, this should be divisible by 7. Then this plus 1 should be divisible by 13, right? Yep. Then 1, 2, 3, 4. This plus 4 should be divisible by 59. And then 6 divisible by 31. And then 7 will be divisible by 19. Yeah. So that's kind of like, so equation then is kind of interesting, right? Our T should be such that 7 multiplied by, let's call it T1 plus, so T is this number divided by 7 multiplied by iteration for this, right? So let's go to I1 multiplied by I1 plus T plus 1 is then, so that's like this essentially then is like a linear algebra problem, because we have this several linear equations here, right? We have then 13 multiplied by, 13 multiplied by iteration number 2. Then we have T plus 4 will be 59, iteration 3. 6 will be 31, iteration 4. And T plus 7 will be 19, iteration 5. Ooh. So that's the thing that we need to solve. In other words, we need to find this stuff such that this minus 1, 59, I3 minus 4, etc. So that's our system of equations. Cakes. Always didn't like systems of equations. I wonder if we can brute force it. So in the above example, bus 87 departs at timestamps 7 minutes after t. This is fine. The only requirement of that method is that the bus ID 19 departs then, and it does. Timestamp. This occurs is, so this is like D, and we have bus 13. Okay, let's also put this here for visibility so we can see it at the same time. So this is an D, departure of bus 7. Then bus 13 departs next minute. So in a minute we don't have requirement. Bus 59. Then we have bus 31 at minute 6, and then 19. Yeah, and there are some departures that don't matter. Here are some other examples. Timestamps. Timestamp, blah, blah, blah. However, with so many bus IDs in your list, surely the actual earliest timestamp will be larger than blah, blah, blah. What's the earliest timestamp such that all of the listed bus IDs depart at offsets matching their position in the list? Yikes. So it's again a nice reminder to us to not try to brute force it, because that will be too big. Positions in the list. So I think there are like two ways, right? We can try to solve it analytically. I guess it's possible, but there is also another way. We can just iterate via iteration numbers. Can we do again the stuff with dynamic programming? Because we can calculate those numbers. We can calculate departure times for a large number of iterations, right? Position. Much of the positions in the list. So here, first of all, we will need to, in any case, change our parser, right? I will not care about doing the proper parse. I will just take bus IDs, because that will still be a vector. But this, by the way, will be also U64 now. So, because otherwise we will run out of numbers quite quickly. So actually, I also wonder if we will even, is that even in U64 range? So I think so, but I'm not sure. This is like 10 in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So like 14, I guess. Let's see, U64 range. Yeah, it should be okay, I think. I think this is bigger. So, is it bigger than this? Yes, it is. It also looks way longer. Okay, U64 should be sufficient here. Okay, so how can we proceed? If we just try to go through like all multiples, all factors for each of the bus numbers, and then check if that stuff matches, that will be very slow, I think. However, we can also go, we can memorize this stuff. Actually, we can just try it, because we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 buses, and 9 buses means for each of those we will need, let's say, we will need to consider iteration like, I don't know, 100,000 for each of those 9 buses. Will it be like some other crazy stuff? I'm not sure. Okay, we can just try and see if it's too slow. We can try to optimize. Otherwise, we can, of course, try to go for analytical solution, but my brain will break very quickly looking at that. I think we definitely will need to calculate it through the factors. So bus IDs will be, we take input, we trim, and we split by n. We skip 1. Then we do next. Do unwrap on that. We do split. Oops. We do split by commas. There is nothing else there. Then we map. So bus. Let's go schedule. Actually, you know what? We will do a bit different thing here. We will do filter map here, and instead we will say, let's call it schedule. So here, schedule. Or, yeah, I will say enumerate, and then I will say filter, and here we will have enumerate adds it as the first. Yes, it's the first, so it will be index element should not be equal to x, and then we map it. So we say here that will be bus ID. This also index, of course. Here it will be index and bus ID parse as u64 and unwrap and collect. So that was our mega iterator. I guess here I need to dereference. Okay, splendid. I will put none here for now, and here, just for the sake of it, let's do schedule. Why don't we like it? Oh yeah, of course, it will be a vector. For now, at least. Should it be a vector? Yeah, I guess. Yeah, it can be a vector. So we will get like this offset as well. So let's see. Yeah, we don't care about index here. Let's make this stuff static as well. So const sample, it's a static string. Right? Right. It's same example here, right? With 7 blah blah blah. Looks like it. Okay. Then here, when we do, let's first do sample. Add line comment. Yeah, I feel I maybe need to update my Rust extension. So let's just do it this for now. Zero at 7, 1 at 13, 59, 4, 60, 31, 6, and 19, 7. Okay, makes sense. Okay, parser works. And now let's try to figure out the algorithm, right? So I guess what I want to try, I want to try to go through I will create a hash map of times where I will store my iterations, essentially, where I put stuff based on like bus ID and factor, and then I will check if its presence there accounting for an offset. Okay, that sounds confusing, but let's just try to write it because I think it will be easier to understand what I'm talking about. Timestamps like departures, I guess, is better, right? Because what we care, so we care about this, like where departure happened associated with buses that depart at this point in time. So that will be a hash map. Okay, we of course need to also add this stuff. Which will be just new thing. And then what will be the type of this hash map? I will just write it down here for simplicity. So we will have departures, which will be U64 mapped to a vector of departed bus IDs. So actually, for example, here it will be 7 and 19. Bus IDs are U64, right? But by simplicity, I will also convert this to U64 so that we don't need to convert later on. So, and then what do we do? So we go by factors. So for factor, starting from 1 to a factor of, because 0, of course, is trivial case, we don't care about it, to a factor of, actually, no, we just loop here again. So we also have, yeah, this, by the way, is mutable, of course. And we also have let mutable factor. So we will need to arrive, like the earliest point where we know the answer is when we arrive at the last bus that departs there, right? So with the largest offset, I guess. So we go with this factor and we then... Oh, I think I don't even need that. I can just go by the largest bus number, I guess. Can I? No, that won't work. Bus 59. Oh, why? Why won't? Because that will be like the least number of iterations, right? 59 compared to 7. So 59 compared to 7 will be like more than 8 times less iterations, which will matter. And then I know that this will be like 4 off the bus 7 timestamp. So I can check for each of those if they correspond to schedule. And I can just go for one bus, right? And then, for example, surely the actual earliest timestamp will be larger than... So if I go with that, how many iterations I will need? I will still need to have extremely large amount of iterations. I guess. Can we also do some more cleverer thing here? So looking at this stuff. If we go from largest bus sequence, and then we look at this number. T plus 6. Like it makes it, of course, way more complex because we have those offsets, right? Can I express my iteration numbers there? I was thinking maybe I can do some kind of search where I switch from like, where I skip a lot of elements and just try to narrow it down. No, it won't work, I think, because it's not non-linear. I think it sounds to me so similar to this data and part 2 tasks, where another approach, like the approach I took was to go through the, we split it like sequence into smaller subsequences, and then we ran recursion normally on each of those, and then we just multiplied results because those were independent. But there is another way of solving this task that I learned about after that when I watched other streamers solving this task, because it was interesting to see if there is a simpler way. And another way is just count a number of ways starting from the last like adapter, and then like seeing which options you have. I'm thinking if there something similar can be done. And I'm also thinking that like multiplying continuously, it's kind of like, oh, I think I start to see something. So T is, no. But I guess, oops, not what I want to do. I want to check linear equations. Equation of a line. Two variables. Blah blah blah. Then it's common to use instead. Tuple is crossover, transforms the equation into true equality. Sure. Function linear algebra. I think I need system of equations. So system of linear equations. Yes. So that's what we have. By the way, let me make it a bit bigger. Yeah. So if you have this stuff, x is essentially 0, right? So like if I try to write it down as a system of equations, what will happen? My first equation then will be, let's try to normalize it, right? So, and I will just call it x1 for consistency with this notation. So let's do this. So you'll have this, actually bus ID1 multiplied by x1 equals to t. And here we have plus 0 multiplied by x2, blah, blah, blah. So essentially all other coefficients there are 0. Then here, what we will have is 0 plus, I will align it so we can see the matrix, bus ID2 multiplied by x2, right? And then we have zeros as well, and this is another thing. So yeah, I think the only reasonable approach here is really to solve the system of equations, something that I never wrote, I think, which is pretty funny because that's one of the first things that people invented computers for. So let's solve the system of equations. Then of course we have 0 here. So I will just do, I guess, no, I will even copy that and say, so you have here and here, we also have a 0. And then we finally have something here, which will be bus ID 3 multiplied by x3 plus blah, blah, blah. C plus 4, etc. So that's how our system looks like. Now, how do we solve it? Equivalent to matrix equation over form. So we take A, which is our coefficients, which are basities with 0. We get like diagonal matrix here, right? So we get A will be equal to bus ID 1, 0, blah, blah, blah. So let's make it like that. And then here we have 0 bus ID 2. It's quite some time since I started linear algebra, so sorry. This is not exactly what I do every day, though. I actually enjoy this stuff quite a bit. Not equations themselves, but like more vector spaces and all the funny factorizations on matrices. It's pretty cool stuff, actually. So that is this, and then we have X, which is of course our, so those are, A is diagonal matrix of bus IDs, and X is iteration factors for each bus, and B is offsets, right? Is timestamp plus offsets. So it will be timestamp plus offset 1. Let's make it like that. Right? So we got a system of linear equations now. How do we solve this shit? So is linear is a summit of values such that the set of all possible solutions called the solution set. A linear system may behave in any of 3 possible ways. The system has infinitely many solutions. I guess that's what we typically get, right? Geometric, general behavior, properties, consistency. Yeah, equivalence, solving, okay. Describing, eliminating. I don't want row reduction. So this is like Gaussian elimination. The linear system is represented as an augmented matrix. The matrix is then modified using elementary row operations until it reaches reduced row echelon form. There are 3 types of elementary: swap the position, multiply a row by a non-zero scalar, add to one row a scalar multiple. There's, oh god. So like, so this is just, yeah, we put like our matrix B here. And then we need to move it to become like this. But that is already kind of the same. Is 1. So we just need to divide by that. Okay, let's in 1 has zeros and all the other entries. So we kind of already close to that, right? It's kind of like special case. I guess it should be simpler. And then we get B. Blah, blah, blah. Is reduced and represents the system. As I show all of the list in has computation written down. equal to 2. 3, 6 plus. Okay, so we got our answers here, which will be our times, and then we need to return the first answer. Cramer rule is an explicit formula for the solution of system of linear with each variable given by a quotient of 2 determinants. For example, is given by the matrix solution. Yes. Finally, if the equation system is expressed as a matrix form, the entire solution set can also be expressed in a matrix form. If the matrix A square has m rows and n equal to m columns, yup, and has full rank, all m rows are independent, yup, then the system has a unique solution given by x equal, unique solution. Oh, okay. X equals to 1, A minus 1 multiplied by B. So inverted matrix multiplied by B. So we just need to invert the matrix. How do we invert the matrix? Matrix, I guess we have diagonal matrix. How to invert diagonal matrix? Let's check. Elements corresponding eigenvalues. So, matrix addition, especially simple for the saving upper left. So bring inverse, invert. The diagonal if only are all non-zero. Yeah, in that case we have diagonal, in particular from the subring of the ring of all n by n matrix. Does it mean that I just need to divide each of those by 1? Is it like that simple? So, because multiplying, then I can just then do 1. I'm so not sure if that makes sense, but I guess 1 divided by bus ID 1. Yeah, and then when we multiply, it's just we multiply by b in this case, which will be this. Multiply on t. Shit, we don't know t. That's the thing. But we can set c to be whatever we want, right? Can we? We can just say, I think so. I'm thinking, I still need to calculate it somehow, right? I know how I can do that. I guess I can take like, I can instead solve it for t dash, where t dash will be this. So this way, I'm guaranteed to always work in normal numbers, right? No, but isn't that just the solution? Is it, okay, we can quickly check it manually. It cannot be that simple. 7 multiplied by, we'll make it smaller. So 7 multiplied by 13 plus 1. Multiplied by 59 plus 4. I'm not sure that I'm doing anything that makes any sense anymore, but let's see. 31 plus 6 multiplied by 19 plus 7. Doesn't make any sense. So we got some number which looks 100. is this number, so this is like the number 106. If that divisible by this, it's not. So those are completely unrelated. It's just not correct, I think. But is that... Gosh, I'm so rusty. I used to be so good at that, and now I'm like, what is happening? I don't know my B, right? I only know that they're related to each other. Can I set it to like 1? Can I say that B is equal to... So like... I'm thinking... Two matrices. Localized version. What am I missing here? I don't want to find those. Do I need for each pass? I don't know iteration factors, and I don't know. I know offsets, but I don't know timestamp, original timestamp. That's actually what I'm trying to find. Iteration. So we have like that additional x there, so that's why we cannot just solve the equation directly. So then oh, I'm also thinking this number. Well, it's not a factor of 13. It's not a factor of 59. It's not a factor of 31 and not a factor of 19. But, oh, okay, I see. That may not need to be the factor, like it is factor of one of those. It is factor of one of those, guaranteed. So we know that this should be divisible by one of those numbers, which means oh, my brain is breaking. I guess as the positions in the list. Can we somehow iterate through possible timestamps? That's the things that I'm thinking about. Like that kind of leads us to this, right? Where I started with this hash map saying that we have U64 and vector of U64, which are like possible factors. You know what? Let's just try to code it and see if it works. I think it won't, but who knows? We can go with our factors. We will arrive at something, I guess, eventually. So what do we do? For each of the buses, we select departures. So for offset bus ID in schedule iter. So I don't want to complicate stuff. I'll just do departures. Factor multiplied by bus ID plus offset is the timestamp for that particular bus. Then we can do departures. And then we can, oh, actually, no, we will do entry where we can say timestamp, or we insert an empty vector. So that will be reference to bus IDs, departed bus IDs. Bus IDs. No, not departed. Or departed. No, departed, we departed. So what I'm trying to do that, so we take factor and bus ID plus offset, that's the timestamp at which bus departs. Then calculate this. We add stuff into this table. Will it help us in any way? I guess not. How do we figure out that we need to break? When we know that when we will need to check all other buses, right? So I kind of made it fast, checking that other buses departed, but it doesn't really help. Nah, it doesn't make sense. Let me try to Google a bit more about the system of equations stuff. Thinking, okay, not the slice type. I think also that reminds me of another thing, right? Which is sieve of Eratosthenes thingy, which is kind of the, is it the same? Well, it searches for prime numbers, but which prime starts in as the first prime number. So it also looks for multiples essentially. Like how does it go? So create a list of consecutive integers, initially smallest, numerate by counting an increment of p and mark them in the list. The smallest number that is greater than p that is not marked. Stop, otherwise p now equals a new number, and repeat from step 3. Number remaining not marked in the list are all prime below n. So, can we use the same algorithm but modify it? Can we just take this and, because that's kind of also what I was trying to do with this hash map thing, we can kind of just go through that, and we will still need to do the offsets as well, but we can also mark them. Know that this is sufficiently fast to also go to pretty high numbers. For large chance range may not fit a memory. Solution is often very segmented sieves, where only portion of the range are sieved at a time. And workers divides range 2 strand into segments. Find the primes in the first segment using the regular sieve. Same being the segment top as well. Find the primes in the set of Boolean array of size. And marking the position corresponding to the multiples found so far, because let's multiple. Oh. I wonder another thing, those numbers that we got, are they actually primes? I think so. Okay, how to check it? Prime, Wolfram Alpha, something like that. Wolfram Alpha. So let's just search here. Oops, 59, I guess. So is prime number 577. Is prime number 61. Oh, okay, I see. So all those things, they're not just numbers. Of course, it made sense, right? That they would be primes, because otherwise it would be weird, since we will be, some buses will always be departing at the same time. But then what we need to find also, there is probably some kind of thing that just solves this. I'm pretty sure there is. So prime stuff. Oh, okay, I found something. That I actually don't know, but that sounds suspiciously close to this stuff. So, states that if one knows the remainders of the Euclidean division with remainder, of an integer n by several integers, then one can determine uniquely the remainder of the division of n by the product of those integers under the condition that the divisors are pairwise coprime. The bound cells by several similar computations of smaller integers. Blah blah blah. Pairwise coprime. What does pairwise coprime even mean? Gosh. False element, yeah, sure, they are. They're just prime, so doesn't matter. The map x, if say n, x modulo n defines a ring isomorphism. Oh, no, we are not going there. So that's pairwise such that and are integers. So those are guaranteed to be integers, right? Those iteration, like a in this sense is our b's, I guess. That for every then there is one and only one integer such that it's division for every a. How to find it? So x is equal a1 by y scope prime such. Does it give me some magical formula? Give me formula. Computation. And easy to check whether the value it suffices to compute. Check successfully. Yes, sure. That I know. That is brute force solution. Yes, this is very inefficient. Exponential time algorithm. True. Search by sieving. The search of the solution may be made dramatically faster by sieving. For this method, we suppose without loss of generality, blah, blah, blah. That implies that the solution belongs to arithmetic progression. By testing the values of this numbers module, one eventually finds the solution. That's the arithmetic progression. Decreased value. 4, 9. Computes the remainder by 4 by adding continues the existence construction is as linear. That's how this thing is called. System of simultaneous linear Diophantine equations. Gosh. Where the known integers are x and the xi's. Yes, that's what we need. Therefore, every general method for solving such a system may be used for finding the solution of Chinese by Smith normal form or Hermite normal form. Okay, we are getting somewhere, finally. However, as usual, when using general being for more specific, it's less efficient than the method based on the direct use of Bezois identity. With greatest than their existing integers, so that more generally, yeah. So following Bezois. Okay, that's like some fancier stuff. This is. So Smith normal form of a matrix is what we need apparently. And this stuff is normal forms that can be defined for any matrix with entities. So it's diagonal, can be obtained from the region by multiplying on the left and right by invertible square matrices. Always calculate if an integer matrix. Let's find a free module. So we have this, yes, and then diagonal satisfy blah blah blah. The elements are unique up to multiplication complementary divisors that can be computed as a1 d where indeterminate divisor greatest common divisor of all minors of the matrix. S and T such that sat is diagonal. This is hardest part once diagonality is achieved. Oh god. Okay, you know what? Oh shit, I need to search here, of course. So I'm thinking about just getting some linear algebra stuff and just making it do this for me. I think that's the easiest solution. So linear algebra. Well, Rust is not Python, so I guess we are not super. There. Oh, last updated 4 years ago. Really? Maybe matrix, Euclid, chunking, and algebra. Ah, that's great, I guess. So, user guide, documentation, splendid. What can you do for me? So it computes like ROP. It doesn't look super big. I don't think it will have stuff that we need. User guide. Okay, this stuff I think we don't really need. Linear systemization. Vector, solve, expect. Holesky, Lopak. Oh, no. Okay. That sounds super complex as well. Shall we try do the sieving things then? Because seems to me this or integer programming. Smith's normal form is those integers. I think this is slightly, yeah, this is slightly too complex for this. It's so funny that they don't really write examples. They write a lot of formulas, a lot of this stuff, but like how to calculate this damn thing. Genius reminder theorem solution, maybe. Okay, look, maybe Wikipedia is not the best resource for that. So solution using the for each compute from I to k. Oh, well, k is number here at least. Compute using a click extended theorem. The integers, the system of congruences. I don't understand this terminology though. System of congruences. It's also a solution. It's equals 2 modulo 5. 35 divided by 5. 7 modules. It's also a solution, so we only need to look for solution modulo. By brute force, you find the solution x17 module. The unique solution up to certain modulus. System of equations has a unique solution. It's trivial. 6 modular, 22 equations in the above form. Okay. Alternatively, what was another thing? They called it Diophantine equation. Okay. How system So, solve. Let's see. Using standard number theory techniques. Thank you very much. That gives me a lot of to go by. Is expression. Yikes. Nope. Vismajewski-Matthews LLL based algorithm. What the hell? How hard it is to solve this stuff. It sounds super simple, but I cannot find any good descriptions of algorithm that don't require me to learn number theory overnight. System, yes, yes. Sure. Sure. Okay, this stuff won't help me. I'm sure about that. I will try to do the sieve because that's something that I at least understand how to do, I think, at least a bit. I need to look up the algorithm again. This stuff I will just ignore for now, I think. Here's an example. Okay. So it's like 1 module 3 for module 5. So this is reminder by module, right? So that's our offsets, right? Begin with the congruence with the largest modulus. You write this congruence as equivalent. So 7j plus 6, yeah, for some integer j. Substitute the expression, by the way, for x, the congruence matrix is the next largest modulus. This expression for x equals 4 module 5, 7 equal 4 module 5. Then solve the congruence for j. J equals 4 module 5. Rewrite this congruence as equivalence reaction for some integer 5k. Substitute 5k into the expression for x. 7 plus 4, 6, 35k plus 34. The expression for x into final congruence and solve the congruence for x. Module 3. Okay. Okay. So we start with the, but that essentially what I wanted to do, right? You start with the largest bus ID. Okay, I think I just wasted a lot of time reading about this stuff because I think I kind of figured out the algorithm already. You take the largest bus ID. We know the timestamp will be multiple of that. We multiply, and then we know that other numbers should also be factors of that, like with the, I wonder how will it help here. 34 module blah blah blah. Yeah. Okay, I guess let's try to just do that. If I'm still understanding that. So that stuff I don't need. Or actually, I also looked at this stuff. Up triangular. So we take you know what? Let's just jump by the factors that we have. I wonder if that will be sufficient. So actually no, still loop. So we will take this stuff. We then take what is the largest in here. So we got a vector of index to like offset to bus ID. Take let maximum. Take schedule map iter map. We take this offset bus ID. We only care about bus ID. And we take max. And we unwrap. We can actually also take max bus max by right by bus ID and drop that stuff. We get max bus ID offset, and we get max bus ID. And then equals to, so times temp will be equal to max bus ID multiplied by factor plus max bus ID offset. What does that like? Do self-compare. Oh man. Oh. Bus ID bus ID2. Gosh, bus. X compare. X can be. Right, that's the thing, I guess. So we get this, and then we need to check. So for this is really dumb, but I guess I had too much reading about Shor or Smith, Hermitian, segmentative stuff, timestamp. So for each of the offset bus ID in schedule, we iterate. And then we just say, you know what? Found. And then if this is offset schedule iter, so let's say true for now. If and here we do factor this, so then we say if timestamp equals to bus ID, no, divided by bus timestamp. So offset then is what? It's we had some x for the so for this we have some max like offset 3, for example, right? And here we got some other offset where we can say which can be smaller or larger. Then timestamp should be equal to timestamp. It will be minus offset. Yeah, should be divisible by bus ID, and if it equals not equals to 0, then we know that this is bonkers, and we can say right. So we found problem, and then if found, say return timestamp. So for now, not really timestamp minus max bus offset sum box new. So this is kind of the thing, I guess. Not exactly, I would imagine, the fastest solution for that, but let's try to see how long it will actually run. Is it correct? I think it was different, no? So it returns something, but that seems to be, I wonder if it's even like the stuff that I want. So what is the largest here? 59. 1, 2, 3, 4. So oh no, that divided by 7. Oh, that's not the REPL I was looking for. So that's the number it returned. No, so it doesn't make sense. Offset. Timestamp plus offset, of course. Yes. Okay, now it looks like it actually runs very slowly, and it probably will eventually return the number, which will be 1 million something. I actually wonder, so like, what will be the factor of minus 4, I think? Yes, minus 4. Oh god, this is still my REPL. divided by 59. Yo. 5. Eh? Ah, plus 4. Oh god. Plus 4, of course. What? Okay, I'm so dumb. This is the number, the timestamp, plus offset divided by bus ID. So actually, so this is too slow. I made a mistake. Timestamp, of course. So here it will be minus divided by 59, right? And 85 minus 4, 81, yes. That looks correct. Almost. 68777. So like I'm almost there. I think I'm failing only at the stuff that I return. So here timestamp, no, I already adjusted for that, so that should be alright. And then here 81. Why? Oh yeah, so that's the correct one, right? Yeah. So we solved it for the test example, but I think for the I wonder now we can use our REPL to see how fast this stuff actually runs. You know what? I will put it into a sample thing. So I have also those sample files, so I can actually run from the REPL and measure the time it takes. So the sample 13, this stuff, right? Then I can remove this and say sample 13. Yeah, sure. So it's a reference, and here it's reference. And we can run this stuff. Okay. And now we then can do this. So we can do day 13, sample 13. Oh, that's the part 1. Part 2. So it's like half millisecond. Okay, that's not too bad. Let's see what happens when we ask it to run for the actual thing. That, I guess, will take some time. So this is that it will be larger than this, multiplied, divided by the largest offset that we have, which is this number. So that will be too many iterations, right? It will be millions, billions, 166 billion iteration. Too slow. How can we speed it up then? Can we somehow jump over some factors? Maybe this stuff kinda gives some suggestion for jumping this larger factor. Because actually also thinking about just solving that by hand, because I think that may be better. So first, let's stop this stuff. Let's make sure that we return the scene in the bug, so I don't need to calculate offsets by hand. And yeah. So that's our magical thing. That's a schedule. Oh, 9. So let's remove this garbage stuff so it's a bit more readable. Okay, no, that won't work, but fine. So then because I'm thinking that I may simplify it a bit, right? If I do a couple of iterations of this thing by hand, I may already simplify, improve the runtime significantly. So what does it say? Timestamp equals 0 module 29 t. So that's the forms they use here. 1929. Module 13. 43 module 17. And t equals 3, 48 module 19. 52 module 23 and 60 module 601 0 no 97 module 37. Okay, so that's like in the how they write this down. Now, so largest module is this, right? So this will be our first one. This will be our second one. And this will be a third. This will be fourth. Well, this stuff runs. I may learn this stuff. So begin with the congruence with largest. Rewrite the congruence as an equivalent equation. So this stuff, we say x. Oops, I can make it smaller. Oh, that's what I wrote here already, right? X1 plus 60. Yeah. Then we have substitute with the next largest module. 4. So you can say that this, we take this one, and then we say that this is Fira code is very useful here because it also allows you to do this triple equals sign equals to 29 modulus this. So that's the second thing, right? So all the congruence for J. 4 module 5. 5. Okay, I don't get it. For x. X is 7. So this we got here, right? J module. Congruence as equivalent reaction. J. But why? Is it like for some integer J? We know that. Oh no, 6-1 is bus city. Yes, this is like iteration one, right? It's x1. I'm dumb. It's not bus one. X1. So for x1, equals to 577 multiplied by this and plus 29. Now substitute this expression for x into the final congruence and solve the congruence for k. For k. Okay. So this is still from 2. For x into the final congruence. X t equals to 601 multiplied by this plus 60. So that will be then, okay, we are getting somewhere, it seems, because this number is significantly larger. So like if I then divide by that, that already looks like doable, I guess. Still will be like 285, but that's already, it's way smaller. So okay, we are getting somewhere. Like I really thinking that I can just hard code it, honestly. So we got this multiplied by this. So it's not very with Rust right now, right? I'm just going like manually and with Elixir, but I think it's better for me. It's faster than trying to learn this stuff completely. 60. Oh, okay. Equation and then solve. So 34 for x. So this is like we can assume that if we would have had a bus with ID this 350,000 something, 239 I mean, then it would have been off by this amount of minutes from our timestamp. And then I wonder, so we can, in principle, add this thing to our vector. We can then, I think, use the existing algorithm we have to just do this stuff, right? So I wonder if it will work. This will be such a ugly hack, but so this is really hard-coded answer, but 60601. Not super proud about that, but what can you do? So this is offset. And this is the bus ID. And then, of course, okay, I guess reference. Yes. Unnecessary parentheses. Sure. So then I guess we should arrive at this. Let's try it and see if it will work. Yeah, let's also make sure that cheating. So day 13 part 2. Yeah, we are cheating. Let's see if it will help us while it tries to do that. Russian congruence for x. For x is x. Ah, that's the last one. So we got this stuff, and we now need to substitute it. So we can take the next one, which will be this, and say the so this stuff plus 41, right? And this will be also multiplied by something like that, I guess. Am I making any sense here? Modules. Business congruence. Solves it. Solved it. That's what's the x. Final congruence 30. We need to substitute that here. So we say 19 multiplied by that is right. Then we can say that this is by e2 41 e2 plus 19. Because I'm thinking that if I simplify by a couple of factors, it should in principle run already better. 41 e2. It's just pretty hard to keep track of that in my head. 19. Yeah. 2. Multiply. It's like, no. 2, which is equal to 19 multiplied by this stuff, I guess. Plus 41. 41, 19, yes. So then this will be 41 plus, oops, this plus 19 . So that, can we even push this? I guess. Push. So first we go offset, it should be this number. Then we get position. Right. Okay, that didn't work out. Let's try again. And by the way, I probably should also just say, let's do debug timestamp, just in case. And debug factor. So factor timestamp. Yeah. So that we can see that I'm not doing something super dumb. Okay, we are moving up quite quickly. So this number is pretty big, I guess. This is already... okay, so it's not still as big. Should I try it again? Okay, we can disable this stuff. So again, letting it run and so it hopefully find something. And here we can try it again. So let's take the next one, which will be 19. So this one. Like, I guess if that won't work out, I will give up this time because I'm a bit too mindfucked already. I want to chill a bit, but let's try. Increasing it once more. So we take this magical expression, right? I hope that I'm correct. I may be like completely already out of solution here. Equals 90 37 y3 plus 97 plus 97 Oh, I guess I may be also wrong about applying that, because just, can I apply it like that, really? Can I just say this is that? Do I do anything useful? Not sure. Well, you can try. Multiply it by this stuff. And then it will be plus 30, so 37 by this magical number plus 97 this, which means we can try offset plus 80. Let's try again. So this is last thing I'm trying. If that doesn't work, I will just give up with the part 2. I will try to solve it a bit later, and maybe we'll review it on Tuesday then, if I will solve it. If not, I will just look up the solution. Because that's not kind of task I enjoy, I must admit. Like, this is just essentially, if you know and understand this stuff, it should be super easy. If you don't, you kind of screwed. It's so, I guess that didn't work out. I either made a mistake or the number is so big that it won't work. Okay. I guess I'm done for today. We failed with the part 2 of day 13. I will read up on that and try to understand it when my head is a bit more fresh. Yeah, that stuff is not some kind of task I really enjoy, I must admit. Part 1 was super simple as usual. Day 12 was also quite simple. And day 11 was also quite simple. So it's really like, if you know some algorithms, it works. If not, it doesn't. I will try to read up on that stuff and hopefully we'll solve it. Until next time, I will stream again on Tuesday. Hopefully I will have a bit more luck with days 14 and 15. And yeah, thank you for watching. Have a nice weekend and see you in 2 days.